All right, so we just finished doing a sort of analysis of the simplest possible model for this very simple 1D case of an iron bar where the right-hand side temperature is held at one temperature, the left-hand side temperature is held at another temperature, and we're looking at how the bar changes in time. We built a really simple single stock model for it, which led us to a single ordinary differential equation, which we found right here. We thought we'd take a few minutes before we go on to sort of develop a more complicated model and work in that direction of actually having a distributed model for this, of asking, well, how does this actually behave? What's this model going to tell us, and what's it not going to tell us? So John, when you look at this differential equation, what are some of the things you see from a sort of mathematics perspective?
Sure. Well, as you said, Mark, first we notice that it is a differential equation for the temperature of the bar, and maybe it's worth me just writing bar here. There are a bunch of constants, right? We've got all of the constants you defined, and we've also got a left temperature and a right temperature, which we're assuming at the moment are fixed.
Right.
Right. So let's do a little thought experiment here, because we should be able to do this irrespective of any model. Why don't we just think about what the temperature of the bar should do over time?
Okay.
Why don't we just draw a little sketch of that?
That sounds like a great idea, John.
Right.
So when you say let's draw a little sketch of that, what do you think we should have as our initial conditions for that sketch?
Right, so we need some sort, and I'll give you the pen, Mark, so I can talk. We need some sort of initial temperature distribution in the bar, and so we can pretty much choose
right now we're
right?
talking now about what we think is actually really happening in the real world. We're not talking about this differential equation.
Correct.
Okay.
We're just really.
All right, so I've got a bar.
Yep.
And we actually said what we thought the initial conditions were. The bar was all at one temperature.
Exactly.
Right? So T bar is equal to T right initially, right? Because the right-hand side, remember, how we say is connected to the outside.
Exactly.
And we stick the left-hand side in this flame, right? So initially, the whole bar is going to be at T right.
Exactly.
Right. So if I plot the temperature versus position for a time equals 0.
Yep.
Well, it's all going to be, if I'll say this is T right and this is T left.
Yep.
The whole bar is going to be just at T right.
Exactly.
Right?
Now, ignoring all we're thinking about models, I'm pretty sure that when we raise the temperature on the left-hand side, I think we all know what's going to happen. And right? We raise the temperature on the left-hand side of the bar, and as time passes, we're going to experience the temperature in the rest of that bar increase.
Yeah.
Right?
Yep.
But let's not forget that we're holding the right-hand side of the bar at a fixed temperature. So it's not like the right-hand side of the bar can increase, but the left-hand side of the bar has to increase,
Right.
which means bits inside the bar have to increase.
Yep. So let me draw something and tell me what you think about this, John. What does that mean? The bar does this over time? Like the whole thing just gradually goes like that?
Well, certainly your final state I really liked, right? Because in the final state, so if we just wait long enough, and we could ask how long is long enough, but let's just say we wait long enough, the left-hand side is going to be at T left, the right-hand side is going to be at T right, and surely the temperature is just going to decrease linearly along the bar.
Yeah.
Right? But I think your question is, how does it get there?
Exactly.
If this picture here was T equal to infinity or just big, right?
Yep.
We just wait long enough. So how does it get there?
Well, I think a problem I have with the picture that I drew is that we're actually saying that we're sort of holding this end of the bar at T left.
Well, that's right. And that's why maybe applying a flame might not be the best model for this,
I think
because it
right.
suggests that you're slowly raising the temperature. Maybe you should think about just putting this in a bucket of hot water.
Okay. So
Put
it's
it in
like
a
so
bucket
I've got
of
like
hot
a
water.
furnace or something in there that's at a fixed
Exactly.
temperature.
Right.
So this left-hand side is actually at that temperature.
It is at
right?
that temperature.
So actually what I could draw, if I sort of were to just to consider that left-hand side, the initial condition might actually look sort of like this, right?
Right.
It's initially just that little tiny bit on the left-hand side is at T left,
Yep.
and all the rest is at T right.
That's right.
Right? And this left-hand side is never going to change, right? Because my initial condition, my boundary condition here
Yes.
is, so this has a boundary condition of T bar equals T left at x equals 0.
Correct. That's right.
Right?
So, and now maybe with this picture, now we can ask ourselves what happens if we just wait a little bit of time,
Right.
right? We could ask ourselves, well, does the temperature way down on this end of the bar start climbing immediately?
But
And if
I've held bars in fire. That's not what happens.
That's not what's going to happen. But if I'm close to this edge, it's going to start
Yep.
climbing, isn't it?
Yeah, this is the edge that's going to get hot faster, because if you think from a physical perspective, remember what we talked about, on this edge you've got a high temperature next to a low temperature, you're going to have a lot of heat flow here, right? Whereas down here you've got cold temperature next to cold temperature, you don't have any heat flow,
Right.
So I think what will happen is that initially it'll start to rise over here, and then as time goes on, and I don't know whether it's I think it must do something like sort of like that.
And like you said, or like we said before, we know that eventually it should just become this nice straight line.
So as time goes on, this function changes like this. Okay, I'll buy that that's what actually happens. Let's go back to the model for a second.
Yes.
So here's our model, right? What does this model tell us?
Good question. So let's think about the long-term behavior first of all,
Okay,
right? In long-term,
let's get another sheet of paper here.
absolutely.
Oh, let's get another sheet of paper that doesn't have crap on it. How about this sheet of paper?
In this room, it doesn't exist.
Go away. All right, so there's our model.
Okay, so let's forget long-term behavior for just a second. Let's ask ourselves about the equilibrium temperature of this bar. Right?
Okay,
now maybe we all use that word differently, equilibrium, right?
Mm-hmm.
So what does it mean to you for something to be in equilibrium? Because you're the weird physicist, electrical engineering guy here.
What's that supposed to mean, man?
Oh, sorry, Mark, you know?
Okay. So what does it mean for something to be in equilibrium? Well, it means that it's reached a point where it's not changing, or it's sort of at steady state, and I'll use steady state in a way that's a little bit sloppy, because I think there's a difference between steady state and equilibrium. Another way to think about it is it's reached the lowest energy configuration of the system. That's maybe not quite what we mean here, but I think if I were to think about what I would mean for equilibrium for this, I would mean what does it get to at the point where it's not changing anymore?
Right.
Nothing's changing.
Nothing is changing. And so how is that codified in our differential equation? For me, that means that the rate of change of the bar temperature and time is 0.
Okay, so at equilibrium,
Yes.
this left-hand side is 0, so we get 0 is equal to 2 kappa C rho L squared TL minus 2 T bar, plus TR.
Yep.
Right?
And notice that since it's an algebraic equation in T bar, we can solve for T bar.
So
And if
T bar is TL minus TR over 2. Right?
Almost, Mark.
No?
It would be TL.
Oh, yeah, you're right.
plus TR,
Thank you. Thank you.
Yeah.
Never do algebra in public.
And notice that that's actually just the average of the left and right temperatures.
Okay. And that's actually, notice, consistent with sort of this value at the middle,
Exactly.
right? Okay, that's
Right.
cool.
So that's cool. So that's the equilibrium temperature. Now we could ask ourselves, or at least one way to query this model is, does this differential equation, is it going to give a T bar that is going to eventually reach this equilibrium, right? So let's think about that for just a second. If we think about that as a differential equation, right, the right-hand side is our rate.
Mm-hmm.
And we can see that there's a left temperature and a right temperature, but then there's a negative 2 T bar, and you've got this stuff out.
So if I were to just write that differential equation out with not worrying too much about, I mean, they're a bunch of constants, right?
Yes.
So I'm just going to collapse them a little bit, and I'm going to say it's equal to some constant a minus some constant b times t bar.
Perfect.
Right? Because I could sort of look at this and say, okay, well, I could collect all of this stuff here. That's a constant, add them all together, I get a, whatever that is. And I collect the other stuff together that multiplies t bar, and that's another constant. So I've got that. And this is a differential equation that I think we should know how to solve, right?
Absolutely.
So what are the solutions for that?
Well, certainly if we just imagine a is 0 for a second, maybe it's worth thinking about that case. If a is 0, this is a really simple differential equation whose solution is an exponential on time, right? So why don't we just write down the solution in that case, Mark, when a is 0?
So for a equals 0, t bar is equal to...
that would be e to the negative bt.
E to the negative b times t. And I guess I can put some constant up front, right? So I'll say...
Yeah, and I think you better put a constant out front because that better be the temperature of the bar initially.
Thank you, John, for that
yes,
excellent catch.
Right. So in the case where this constant is 0, and we can deal with the other case in just a second, we see we're just going to, the temperature, assuming this is some positive value, is just going to exponentially decrease in time.
Right. And it'll eventually end up being 0.
And it's going to go to 0.
Yep.
Okay. And that was for the a equal to 0 case. Now let's think about the a not equal to 0 case.
So if a is not 0, then let's see. What does t bar have to be?
Well, could we just, without going through any formal steps, could we just adjust this solution to take care of that? I bet you we could. Why don't we just take this old solution and then add on a? Does that make any sense?
I think that does. I seem to remember something about homogeneous and inhomogeneous and things like that from a class long ago. But
from a class long ago. We could check, right?
Yep.
We could check if this is the solution by doing what? We could plug it back into our differential equation.
Yep.
And see whether or not it works.
Yeah, no, it's worth noticing that like this T naught takes on a bit of a different meaning here, right? Like here it is the initial temperature, and here actually A plus T naught is the initial temperature. But okay, but certainly I buy that it works.
Well, I don't know if you should, because I did suggest we should check.
Okay.
Is it worth checking?
I think we should.
What is it that convinces you that it's right, Mark?
Honestly, John, I didn't think about it.
That's right. Well, for example, one of the reasons why we know it's not right, is if we think about the equilibrium temperature of this bar, with everything in this form, we want to set this equal to 0. So what's the equilibrium temperature of the bar? It should be A over little b. Right?
Yep.
And we expect this bar, temperature of the bar, to evolve over time so that it becomes that equilibrium temperature. And this equilibrium temperature is A. So there's something not quite right.
I'll just put an over B there and that'll fix it.
Awesome. What a great fix. Is it good enough? I've got a better idea.
All right.
Why don't we just do something a little bit different? Because I think we want to get this right. Right?
Sounds like an excellent idea.
And we know, everybody knows that if we want to get it right, we don't let Mark Somerville do it.
Particularly not on camera.
Yes. Why don't we think instead, so in this simple model, T equilibrium is A over B. Why don't we think instead about the evolution of not the bar temperature, but the difference between the bar and the equilibrium temperature.
Were I not on camera, I might have actually thought to do that.
Yes, you might have. And I'm just going to call that temperature T.
Yeah.
Right. T difference. It's the difference between the bar and the equilibrium. Okay, so I'm actually going to think of this the other way, and I'm going to write T bar as the equilibrium temperature plus a difference. Okay. I'm going to substitute this into our differential equation. So really what I'm doing is I'm making a change of variables that we've thought about in the past. just because we want to get this one right and be careful. Okay, so I'm doing a little bit of algebra here. I'm re-expressing T bar as the sum of two temperatures, one of which is going to be the equilibrium temperature, and the other one is going to be a temperature that evolves in time. When I take the derivative with respect to time, the equilibrium temperature doesn't depend on time. So that is, the left-hand side just becomes the rate of change of this difference. And on the right-hand side, if we multiply this out, right, you'll notice you get two terms. And I'm grouping them separately because this one is actually 0 by definition.
Yep.
Right, because that's how you define equilibrium temperature. So actually, if you make this change of variables, so if you just think about it slightly differently, you see...
Or if you just think about it.
Or if you just think about it, you see that the temperature differential is governed by a really simple differential equation, which has a solution that we're all used to, which is the exponential solution. And then if we like, we can undo that transformation and rewrite everything in terms of the bar temperature. And it's probably worth doing that. So this is T bar minus T equilibrium equals the initial temperature. So that's actually the initial temperature of the bar minus T equilibrium times e to the negative bt. Okay. So when we are done, oh, and we just moved off the side of the page, sorry about that. The temperature of the bar over time is nothing but the equilibrium temperature plus this difference. And it's that difference that decays exponentially in time. And that brings us back to the picture that you had earlier, Mark, right? Because you said if we think about this as the difference between the bar and the equilibrium temperature, our solution tells us that that difference, which was up here, should decay exponentially. Right? And so if I thought about the temperature in the bar right here, if we just examine it here, we should see that this temperature, if I just think about it as a function of time, should be decaying exponentially to the equilibrium.
Right. So if I were to actually sort of take that cut.
Yeah, let's cut at that point.
Cut at that point, and instead of plotting temperature versus position, I'm going to plot T middle.
Exactly.
Versus time.
Yes.
Right? So my final equilibrium value here, we already figured out, was T left plus T right
over 2
divided by 2.
Yep.
And it's going to exponentially approach that, right? It starts at T right because the bar was initially at T right, and it rises and exponentially approaches that.
Absolutely.
Okay. So notice the insight we've gotten from this model now is we have some sense about how the temperature kind of at the middle of the bar, or the average temperature of the bar, changes over time. So a sort of plus of this model is some time insight. But a significant negative of this model is we have no spatial insight. Right? We know that, in fact, the real system is spatially distributed. The temperature changes in different ways at different points in the system, but our model doesn't have that at all because we chose to just use a single stop model.
And maybe it's time for us
It is definitely time for us to stop this video. It is way too long, but I'm sure you'll enjoy watching me make a fool of myself, so hopefully those of you that get to that will enjoy that.